Welcome to The Explainer, everyone. I am so thrilled to have you here today because we're tackling a topic that has, quite literally, rewired the world we live in. We are going to completely demystify machine learning, and we're going to do it by stripping away all those dramatic sci-fi movie tropes of sentient robots, and instead, we're zooming in on the fascinating, grounded reality of how these systems actually work. So, if you've ever wanted to look under the hood of the algorithms that drive our daily lives, well, you're in exactly the right place.
Okay, let's map out our journey today. We've got 5 main stops: decoding machine learning, taking a quick journey through its history, diving into supervised and unsupervised learning, exploring reinforcement learning, and finally wrapping up with some really cool real-world applications.
All right, Section 1, Decoding Machine Learning, stripping away the sci-fi tropes. To really decode what machine learning actually is, which at its absolute core is a system that learns patterns directly from data rather than relying on explicit hard-coded rules, we have to look at Arthur Samuel's incredible insight. Think about this for a second. In 1959, while working at IBM, he realized that a machine could be programmed to learn how to play checkers better than the human who wrote the code. That was a total game changer. It established the ultimate goal, a machine generalizing data to autonomously outperform its own creator's manual abilities.
Moving right along to Section 2, A Journey Through History, the long road to modern AI.
Tracing this timeline is just absolutely fascinating because it really puts things into perspective. Way back in 1943, Warren McCulloch and Walter Pitts actually developed the first neural network using an electric circuit, proving machines could communicate without human interaction. Then, by 1957, Frank Rosenblatt created the perceptron, this early algorithm using artificial neural networks to improve computer predictions. But it wasn't exactly smooth sailing from there. From the late 70s through the 90s, we hit what's known as the AI winter, a really tough period where the hype totally outpaced reality, funding dried up, and progress kind of just stagnated. But the field persevered. The big turning point? 1997. That's when IBM's Deep Blue defeated chess grandmaster Garry Kasparov, proving to the whole world that an AI system could actually surpass human understanding in incredibly complex tasks.
Which brings us to Section 3, supervised and unsupervised learning, the 2 main engines of learning. So before we jumped into the algorithms themselves, we really have to define our data. Why? Because the data completely dictates the method. On one side of the coin, we have labeled data. This data provides an explicit answer key for the machine. It's like showing the computer a picture of an animal that has a tag specifically saying, "Hey, this is a cat." On the flip side, we have unlabeled data, which is nothing but raw input variables. Think of it as a giant pile of images with absolutely no tags or hints whatsoever.
When you contrast these directly, the learning paradigms become crystal clear. Supervised learning acts kind of like a teacher guiding your predictions. You feed it that labeled data, and it learns to predict a known quantity, like identifying that cat. Its whole job is to minimize the error between its prediction and the known ground truth. Unsupervised learning, though, totally different ballgame. No teacher, no labels. It essentially forces the machine to analyze raw data and discover its own hidden intrinsic patterns or groupings entirely on its own.
And this brilliantly illustrates what unsupervised learning actually looks like mathematically. Just look at how scattered data points, which initially came with 0 labels, are handled. An unsupervised clustering algorithm analyzes the proximity and similarity of these raw features and automatically groups them into distinct clusters. It literally finds order in the chaos. And that is incredibly powerful when you're dealing with massive data sets where human observation would totally miss the underlying structure.
All right, Section 4, Reinforcement Learning, learning by trial and error.
Now, this third main engine totally flips the script. It trades static data sets for interactive environments. Unlike the models we just talked about, reinforcement learning doesn't rely on a direct ground truth or predefined labels at all. Instead, it relies strictly on learning by trial and error. The programmer sets up a system of rewards and penalties, and the model, which is usually called an agent, learns to make sequences of decisions by evaluating its current state and taking actions that will maximize its reward over time. It's like teaching a dog a new trick with treats.
What's really interesting here is how cleanly we can map out this continuous loop. The learner, or the agent, observes a state in the environment. Then it takes an action. Based on that specific action, the environment spits back a reward signal, which could be positive or negative. The agent then updates its policy, its internal strategy basically, to favor actions that yield better rewards in the future. This holistic trial-and-error approach is exactly how we train AI to play incredibly complex video games or operate autonomous robotics.
Finally, Section 5, Real-World Applications, from theory to modern practice.
So how does all this theory actually play out in the real world? Well, these distinct paradigms are perfectly suited for entirely different business problems. Supervised learning models, because they have that reliable ground truth, are perfect for accurate classifications, like filtering out your email spam or diagnosing medical images. Unsupervised learning, with its superpower of clustering and finding hidden links, is the absolute engine behind e-commerce recommendation systems, finding those overlapping shopping habits you didn't even realize you had, and reinforcement learning. That's out there right now training complex robotics in simulated environments before they ever hit the real world.
But hey, it goes way beyond just corporate applications. The impact this is having on modern research is just staggering. The tangible benefits of extracting insights this quickly allow researchers to tackle massive, unprecedented projects. We're talking about using machine learning to parse through absolute mountains of satellite data to accurately estimate land coverage. We're tracking social media data in real time to understand and mitigate public emergencies. It's being used to classify vast amounts of text data to understand economic activity and even to deeply personalize education by tracking and adapting to an individual student's learning progress. Automation at this scale is completely revolutionizing how we interact with information.
And that brings us to a really crucial question. The landscape is shifting rapidly, right? As we enter this 2026 AI-first landscape, the old way of, learning just the math for a year before even touching AI, that's completely outdated. Today, learners are using AI assistants to generate code and prototype at lightning speed. But here's the catch. You absolutely cannot sacrifice your understanding of the fundamentals. So my question to you is, how are you going to combine the speed of these incredible new AI tools with the rigor of classical machine learning evaluation? How will you ensure you aren't just copy-pasting code, but truly verifying your models using robust metrics like train test splits and confusion matrices in your own workflows? I really encourage you to take this challenge head-on. Build a hybrid project. Put these paradigms to the test. Keep learning, keep evaluating, and I will see you on the next explainer.